On to Chapter 20, the chi-square test of independence. The chi-square test of independence is based on the chi-square distribution, which we talked about in Chapter 19. It is probably the best known of all of the different significance tests, and it indicates the probability that association between two categorical variables is due to chance alone. Now, to demonstrate the chi-square test of independence, and I think I'll just go ahead and call it the chi-square test, we'll use an example that was presented in Chapter 7. So in our special needs adoption study, we have three groups of family ethnicity. The study looked at whether a child had serious behavior problems or not as perceived by the responding adoptive parent. And I'll describe the results presented in this cross-tabulation from the perspective of having serious behavior problems. And the results that were obtained were that percentages differed in the three family ethnicity groups. Among the three groups, children placed in minority in-racial families. So here we have a minority family and the child is the same ethnicity of at least one parent. Only 29% of responding parents report serious problems. In the white in-racial families, this percentage is 47. In the transracial adoptions, it's 37%. So the percentages with serious behavior problems differ in the three groups. And the question is, are these differences in percentages large enough so that given a true null, you wouldn't expect to find these differences simply due to the luck of the draw? With a chi-square test of independence, you really can think of the null hypothesis in two ways. I mean, the first way to think of, and I mean to say you can think of the hypothesis pair in two ways. The first way to think of it is to conceptualize the null as asserting absence of association. So that you would then have the pair where the null states in the population from which the study sample is selected, two variables are unassociated, and then the alternative simply states the opposite. So in this population, two variables are associated. Now recall that with categorical variables, equal percentages convey absence of association. So another way to think about the hypothesis pair is to think about it in terms of percentages. So if you think about the hypothesis this way, then the null states that in the population from which the study sample is selected, percentages are equal, and the alternative states that this is not the case. And indeed, you know that it's possible that percentages could be equal in a population, but even so, due to luck of the draw, you could get differing percentages in your random sample. So that's the question that this test is tackling. So let's talk some about the chi-square test of independence. So you know that degrees of freedom are the number of independent values after mathematical restrictions have been taken into account. So degrees of freedom for the chi-square test of independence equal r minus 1 times c minus 1, where r is the number of rows and c is the number of columns. So our example has two rows. In other words, the top row was child has serious behavior problems, the bottom row child does not. And then we have three columns, those corresponding to the three categories of family ethnicity. So carrying out the multiplication, our example has 2 degrees of freedom. Now, just as is the case with the one variable chi-square test. When the null is true, the researcher expects the value of the obtained chi-square to be reasonably close to the number of degrees of freedom. When the null is false, one expects the value of chi-square that is computed to be greater, often considerably so, than the number of degrees of freedom. So you encountered observed and expected proportions and observed and expected frequencies for the one variable chi-square test, and these same terms come up again for the chi-square test of independence. Observed proportions are the actual proportions. So, focusing on the top row, our observed proportions are 0.29, 0.37, and 0.47. And here are those proportions expressed as percentages. But we'd simply divide the percentages by 100 to convert to proportion. Now, the expected proportion, and these are always going to be expected column proportions given how tables are structured in this text. So the expected proportion is the proportion expected given a true null. And expected proportion is computed by dividing the row margin total by the sample size. Expected proportion is going to be identical for all cells in a given row. So, I mean, it will be the same for each of these three groups in our example. And it will be for each of these cells 273, that being the row margin total, and we're going to divide by 671, that being the n for the crosstab table. So that yields an expected proportion of 0.407, about 0.41 for each of the cells in the top row. Observed frequencies are simply the actual frequencies in a given cell. So for instance, the last slide conveyed to us that there were 59 minority in-racial cases with serious problems. Observed frequency for that cell then therefore would be 59. Expected frequencies are the predicted frequencies given a true null. To calculate expected frequencies, multiply the row margin total by the column margin total and divide by the sample size. So here is a calculation of expected frequency for the bottom right cell. So the sample size is 671. Here's the row margin total. Here's the column margin total, and the calculation yields an expected frequency of 32.03. So expected frequencies don't always compute to whole numbers. You can have decimals. And again, here's a look at our cell here. So we multiplied 54 times 398 and divided by 671 to get our expected frequency of 32.03. And the crosstab table here shows the expected frequencies for each cell in our crosstab table. So for instance, here we're multiplying row margin total by column margin total, dividing by 671 to obtain the expected frequency of minority in racial cases with serious behavior problems. Chi-square test of independence uses the same formulas as does the one variable chi-square test. So here is the preferred hand calculation formula, and it makes use of observed and expected frequencies. Now, results will be sufficiently accurate for a 2 by 2 table when the average expected frequency is greater than or equal to 6, and the minimum expected frequency is greater than or equal to 1. Both of those conditions should be met. And for all other tables, in other words, for all larger tables, the average frequency should be greater than or equal to 4, and the minimum expected frequency should be greater than or equal to 1. Now, in our example, to calculate the average expected frequency, we're going to take the sample size and divide by the number of cells. So our average expected frequency computes to 111.8. Our minimum expected frequency is 21.97, and that is the upper right cell. So here's our upper right cell in our computation of 21.97, and you can see that is the smallest of the expected frequencies. The key point is that our guidelines are met, therefore results will be sufficiently accurate, and we can proceed with our chi-square test. First step in the hypothesis testing model is to state the hypothesis pair. So as you recall, one can state that pair in terms of the presence versus the absence of association. So I'll read the null. In the population from which the study sample was selected, family, ethnicity, and the presence of a serious behavioral problem are unassociated. And the alternative would state that these are associated. One can also state the hypothesis pair using percentages or proportions. So, in the population from which the study sample was selected, the percentage of children with serious behavioral problems is equal in each of the 3 family ethnicity groups. And then the alternative could be stated to say that this percentage is not equal in all 3 groups. The second step in the model is to select a significance level, and we'll use the 0.01 level. The third step of the model is to carry out the test, and we'll use a grid similar to the grid that we used for the one variable chi-square test, and things proceed essentially in just the very same way. The difference is rather than dealing with for instance the 4 different groups that we had in our example for the one variable test, and I think these were black, Hispanic, white, and other ethnicity. Well, instead our rows comprise the 6 cells of our crosstab table. So let's go ahead and demonstrate a calculation. So for the upper left cell, we observed 59 cases. The expected frequency was 81.78. We subtract the observed from the expected to get minus 22.78. We square that to obtain 518.93. We divide 518.93 by the expected frequency, 81.78, and that yields 6.35. And we'll talk through one other cell. So the lower middle cell had an observed frequency of 222, an expected frequency of 246.75. The subtraction yields minus 24.75. We square that to obtain 612.56. We divide by 246.75 and we obtain 2.47. And then the summation sign here directs us to sum the values of the final column for each of our cells. And so we do so, and these values sum to 17.09, and that is our obtained chi-square, the chi-square that we calculate. The final step is to is to make a decision on the hypothesis pair. Recall that our degrees of freedom are 2. We're using the 0.01 level. So the appropriate cell in the chi-square distribution table to find is the one I'm circling here for the 0.01 level, 2 degrees of freedom. The critical value of chi-square is 9.21. The decision rule calls for us to reject the null if our obtained value exceeds the value in the table. So our obtained chi-square is 17.09, and that does indeed exceed 9.21. Therefore, we reject the null. We conclude that chance alone is an unlikely explanation for the differences between the percentages of kids with serious problems in the 3 family ethnicity groups. So here are our results presented visually. So here's our obtained chi-square, a little bit greater than 17. Here is the critical value of chi-square at the 0.01 level for 2 degrees of freedom at 9.21. And you can see that we are indeed in the rejection region. I mean, our obtained chi-square far exceeds the critical value, and hence we reject the null. This figure is showing you a chi-square distribution with 2 degrees of freedom, and perhaps you recall visually that the prior chapter showed you chi-square distribution with 3 degrees of freedom, so you can consult that one and you'd see that these two distributions have different shapes. And indeed, as I mentioned earlier, there's a different chi-square distribution for each different degrees of freedom. Now, all we can tell from consultation of the chi-square distribution table and from looking at this figure is that our obtained chi-square is greater than the critical value of chi-square from the table, so that therefore the probability of our result is less than 0.01. But we cannot determine the exact probability of obtaining our result or a more extreme result. I went ahead and used the SPSS statistical software package to carry out the chi-square test in this example, and the p-value that the software package yielded was 0.00019. So thus, given a true null, results as extreme as or more extreme than our result would, in other words, large differences in percentages between groups larger than those that we observed with our given sample size. Such differences would occur only 19 times in every 100,000 random samples. So we can be very, very, very next to certain that our results are not simply due to sampling error. Now, the hypothesis pair for the chi-square test of independence is always non-directional. However, if you have 2 dichotomous variables, in other words, if you have a 2 by 2 table, you can formulate a directional pair. So suppose that you had program A and program B, and that your dependent variable is successful versus non-successful outcome. So each variable then is dichotomous. That being so, you could formulate a directional pair. For instance, you might formulate this pair. The null percentage of successful outcomes in A is less than or equal to that in B. Alternative percentage of successful outcomes in A is greater than in B. Presume that you carry out the chi-square test by computer, or according to, or you could use the table here. Now the computer would give you the exact probability. If the computer calculated a probability for you of p equals 0.08 to determine, in essence, a directional p, that is the p that would correspond to the directional pair, and this pair is only going to make sense in the 2 by 2 table, you could divide the p given by the computer program in half. So if the computer program generated a p of 0.08, and if you've got a directional pair and results are in the expected direction, then the directional p, which is to say, the directional p would be 0.04. And so actually, if you were using the 0.05 level, you could reject the null for a directional pair. And there's a footnote in Chapter 20 that talks a little bit about this. Here is just an example to reinforce that the chi-square test is a statistical significance test. It's not a measure of size of association. I mean, chapters 6 through 9 of the text presented various measures of size of association. That is to say, the degree to which values of one variable tended to go together with values of another. Now here we have two experiments, and everything is identical in the two experiments except for sample size. So this first experiment has a total sample size of 40, 20 in each of two groups. The second experiment has a sample size of 400, 200 in each of the two groups. Now in both experiments, size of association is identical. So let's look at size of association using the differences in percentages measure. So in the first experiment we see that 16 of 20, which is to say 80% of method A cases experience success versus 12 of 20, or 60% of method B cases. So the difference in percentages here, our measure of size of association computes to 20%. So here our percentages are identical. So in the second experiment it's also the case that 80% in A versus 60% in B experience a successful outcome. I mean, it's 160 of 200 in A and 120 of 200 in B. But the size of association in this second experiment, as measured by difference in percentages, is exactly the same as in the first experiment. The difference in percentages computes to 20%. Now, let's go ahead and calculate chi-square. And you're not going to see these calculations, but we'd carry out the calculations using the formula as just presented, and the chi-square in our first experiment would compute to 1.90. The chi-square in our second experiment would compute to 19.0. Now we would reference the chi-square distribution table for 1 degree of freedom, or I mean, better yet, we would use a statistical software package to carry out these tests. So the probability that the difference in percentages is due to chance alone in our first experiment is 0.17. The probability that it is due to chance alone in our second experiment is 0.0001. So why do these probabilities differ? Size of association was identical in the two studies. And so this ties in with the sample size and sampling error. I mean, we have a much larger sample in the second experiment, so the sampling distribution is much tighter, and smaller differences, or we can say weaker and weaker relationships, result in statistical significance as your sample size goes up. So there simply is much less sampling error in this second study than in the first. And so we reject the null in the larger sample study, but fail to do so in the first experiment. But I very much think it's important that you look both at size of association. So here you look at size of association, and referencing the table in Chapter 6, a difference of 20% is characterized as a medium-sized difference. So you take that information into account. That's important information. And then you also look at the statistical significance. So here we're seeing a medium-sized association, but no statistical significance. Here we're seeing a medium-sized association, but the result is strongly significant. Obviously, our statistical power is much larger in the second study. So why aren't we getting a statistically significant result in the first study? Well, ultimately, we don't know, but it's the case that with larger sample size, we'd have greater power and a greater opportunity to find a difference, if indeed it did exist. But in some statistical significance tests, of which the chi-square is one, tell you whether your study sample result is likely to be due to chance alone, and that's not the same thing as size of association. Your measures of size of association tell you that, and I think both of these are important things to look at. Our next chapter is looking at analysis of variance, which examines differences between two or more sample means.